Welcome back to our channel. In today's video, we're diving deep into insulation testing, one of the most important steps in ensuring electrical safety and equipment reliability. We'll cover everything from what is insulation testing, various tests involved, how to perform an insulation test correctly, how to interpret your test results, and much more. So make sure you watch this video till the end, because by the time we're done, you'll have a complete understanding of insulation testing, from basics to best practices. Let's get started.
All right, let's dive in. Today, we're basically becoming high-voltage detectives. We're going to uncover the invisible science that keeps our world from, well, short-circuiting. It's what prevents catastrophic failures in everything from power grids to transit systems. And it all starts with one really important question. So think about it. What exactly is keeping thousands of volts of raw, dangerous electricity from just jumping wherever it wants to go? The answer is something we all depend on literally every single second of the day, even if we never see it. And that something is electrical insulation. It's this invisible guardian, right? It's wrapped around every important wire, every component, and its entire job is to be a barrier, to stop electricity in its tracks. But here's the catch. This guardian isn't immortal. It gets old, it gets dirty, and eventually it can fail. Over time, things like moisture, pollution, even just big temperature swings, they all team up to attack the insulation. They create these tiny invisible weaknesses, and slowly but surely, they turn our silent guardian into a ticking time bomb. So what it all boils down to is this one simple idea: resistance. Healthy insulation is like a super strong solid wall. It has incredibly high resistance, so electricity just can't get through. But when that insulation starts to fail, its resistance drops. That solid wall starts to get leaky, allowing little bits of current to escape. And that, right there, is the beginning of a very, very big problem. So how in the world do you figure out if this invisible guardian is still doing its job? I mean, you can't just look at it and tell. You actually have to ask it a question. And the way we do that is with a very high, but very controlled DC voltage. It's actually a surprisingly elegant way to give it a quick health check. The whole process is, at its heart, pretty simple. First, safety first, right? You disconnect the equipment from power. Then, you apply that specific DC voltage. And finally, you just measure how much current, if any, is leaking through. If there's a tiny leak, that means you have high resistance, which is great. But a bigger leak, well, that means low resistance and you've got a problem. Now, performing this kind of high-stakes checkup requires a pretty specialized tool. You can't just grab any old meter. You need something like this, the Metrel Teraohm 5kV. And honestly, the best way to think of it is like a doctor's diagnostic kit, but for our most critical electrical systems. It's designed to do a full physical, not just take a temperature. And believe me, this thing is way more than just a simple meter. It can measure resistance into the teraohms. That's trillions of ohms with a T, all while applying up to 5,000 volts. It runs all these advanced diagnostic tests, it graphs the results for you in real time, and, this is absolutely crucial, it makes sure the equipment is safely discharged when the test is all done. But here's the thing, a single one-off measurement doesn't always tell you the whole story. To really understand the health of an insulator, you need to dig a little deeper, and this is where the full diagnostic toolkit really comes into play. So the first tool in the kit is your basic insulation resistance test. The easiest way to think about this is like taking the insulation's temperature. It's a quick spot check, gives you a value at one specific moment. It's essential, yeah, but it's really just a snapshot. To get a much deeper diagnosis, we use something called the polarization index, or PI test. Now, this test is fascinating. It doesn't just measure the resistance, it's actually measuring the quality of the insulation material itself. See, inside good, clean insulation, when you apply voltage, the molecules inside slowly align themselves to the electric field. And get this, that alignment actually increases the resistance over time. The PI test is designed to measure that improvement. And what's great is that this kind of abstract science translates into a super clear, easy-to-read diagnosis. A low PI value tells you the material is probably contaminated or degraded. It's just not polarizing the way it should. A high value, on the other hand, tells you the insulation is clean, dry, and in really good shape. But what about hidden flaws? Tiny cracks or pockets of moisture that only cause a problem when they're under serious electrical stress? For that, we need a stress test. The step voltage test does exactly what it sounds like. It methodically steps up the voltage, pushing the insulation to see if it can handle the pressure, or if it starts to crack. So here's how that stress test works. The voltage is applied in 5 equal steps, over 5 equal chunks of time. It just ramps up and up and up, all the way to the maximum test voltage. And at every single step, the device is carefully measuring that resistance, just watching for any sign of weakness. Okay, so we've poked and prodded the insulation, we've asked it all these questions. Now it's time to actually interpret the answers. This is the moment where all that invisible data gets turned into critical, real-world decisions about safety and reliability. In a perfect world, as we ramp up that voltage, the resistance should just stay incredibly high and rock-solid stable. But what happens when there's a hidden flaw just lurking under the surface? Let's watch it play out. At the first step, 1,000 volts, everything looks amazing. The resistance is 20 gigaohms. That's 20 times billion ohms. Seems totally healthy, doesn't it? So we keep going, we ramp up to 3,000 volts, and the resistance is still holding steady, 19.9 gigaohms. Honestly, if you were just doing a quick spot check, you'd probably stop right here and say, yep, we're all good, but this stress test isn't over yet. And then we hit that final step, 5,000 volts. And whoa, look at that. The resistance just falls off a cliff, plummeting to 2.5 gigaohms. That's it. The stress test just found a critical weakness, a breakdown that only showed up when it was pushed to the limit. That's the hidden danger we were looking for. And the official engineering guidance on this is about as direct as it gets. This result isn't just a number on a screen. No, it is a clear, actionable signal. It is telling you, hey, this insulation is compromised and you need to replace it before it fails. And really, at the end of the day, that's why all this matters so much. This kind of diagnostic work isn't just some technical exercise for engineers. It's fundamental to public safety. It's about preventing blackouts. It's about keeping all the complex systems that power our modern lives running safely and reliably, day in and day out. It really makes you wonder, doesn't it? What other invisible tests and silent guardians are out there right now, working behind the scenes just to keep our world running? Something to think about. Thanks for tuning in.